We will start today power electronic circuits and equipment. Depending upon the function, the entire power electronic circuits or equipments can be classified into 5 groups. The first one, they are known as the converters. The input voltage is AC, output voltage is DC. When I am saying output voltage is DC, it means that average value of the output voltage is finite. It's not necessarily a constant value. Okay. The second one is inverters, wherein the input is DC, output is AC. What comes to your mind when I am saying output is AC? Is it a pure sinusoid? No. When I am saying when the output is AC, it means that average value of the output voltage is 0, not necessarily a sine wave. Third one, input is DC, output is also DC. This output voltage can be varied. It could be either choppers or switch mode power supplies or DC to DC converters or DC transformers. The fourth one, input is AC, output is also AC, but the frequency of the output voltage is same as the input, whereas the magnitude is changing. These are known as phase controllers. They are often used in fan regulators. You might have seen a small regulator, but just by changing the knob you are varying the speed. They are basically phase controllers. The last one, input is AC, output is also AC, both voltage and frequency are variable. They are cycloconverters, a new group of power electronic equipment. They are also known as matrix converters. So last one is cycloconverters and matrix converters. We will study each one of them in detail. Okay. First one, converters. What are the basic assumptions that are we making? All the devices and the circuit components are ideal. In other words, when the device is conducting, voltage across the device is 0, and when the device is open, when the current flowing through the device is 0. And when I am saying passive elements, L is a pure inductor, C means a pure capacitor, and input is a pure sine wave. Okay. The first one is diode circuits. A low power, a 3 ampere 600 volt diode, 2 element device, anode, cathode. A 40 ampere 600 volt device. What exactly they mean, I will tell you later. Anode, cathode. This device cannot be used in a circuit. This has to be mounted on a heat sink. This is a heat sink. It has to be mounted on a heat sink like this. So cathode, anode. Body is anode, this is a cathode. Since it is a 2 element device, these are known as the uncontrolled device. Hence the name uncontrolled rectification. Let us see what are the various parameters. Alpha is the angle at which diode starts conducting. Beta the angle at which diode stops conducting. So, what is the conduction angle? It is beta minus alpha. All these angles alpha and beta are measured with respect to the positive zero crossing. Okay. Half wave rectifier. There is only one diode connected in between the source and the load. We will consider first load to be a purely resistive. Input is a ideal sine wave, a pure sine wave. Device is ideal. So, diode starts conducting at the positive zero crossing. When the diode starts conducting, output voltage V naught is same as the input voltage. Load is purely resistive. We know that current and voltage are in phase. KVL says Vi is equal to I into R, or Vm sin omega t is equal to I into R. So, current is also sinusoidal, reaches peak when omega t is equal to pi by 2. At omega t is equal to pi, voltage becomes 0, current also becomes 0, diode turns off. So, alpha is 0, beta is equal to pi radians. So, duration for which diode conducts in each cycle is pi radians. What happens in the negative half? There is no current flowing in the circuit, current becomes 0 at pi, anode potential becomes negative, diode cannot conduct. So, in the entire half, diode is in blocking mode. So, input voltage comes across the diode. So, the entire voltage the diode has to block, or the voltage rating of the diode should be a minimum, should be Vm. So, if input is 230 volts, the peak of the input will be 230 into root 2, that is around 310 volts or so. So, when I said 40 ampere 600 volt diode, it means that it can carry 40 amperes and it can block 600 volts. Okay. It can block 600 volts. In other words, peak reverse voltage that can be applied theoretically is of the order of 600 volts. Okay. So, these are the various equations, simple equation that I have written. What is the average value of the output voltage? I said AC to DC rectifier, DC converter, output voltage has a finite DC value. The average value is given by Vm by pi. So, it is output voltage is not a constant DC. It is varying from, output voltage varies from 0 to Vm and to 0 in 0 to pi radians, and continues to remain 0 till pi to 2 pi. So, average value, if I integrate it over the cycle, it comes to Vm by pi. It also has other AC components. If I write a Fourier series of this, it is an even function. So, has a average component and other even frequency components. So, what is the RMS value? RMS value is Vm by 2. I said output voltage is not a constant DC, it has a AC components. The measure of AC components in the output voltage, they are known as the ripple voltage, is given by this expression. And what is the ripple factor? Ripple factor is measure of the AC components in the output voltage to the DC value. It is as high as 1.21. Okay. We have discussed about the resistive load. Now we will replace the resistive load by a pure inductor. Input is a sinusoid. Again, diode starts conducting at the positive zero crossing. When the diode starts conducting, the circuit equation is Vi is equal to V naught, that is equal to L di by dt. So as the input voltage increases, current also will increase. Will it reach peak at omega t is equal to pi by 2 as in the case of a resistive load? No. It will reach peak when the input voltage is 0, or it will reach its maximum when omega t is equal to pi. Why am I saying this? See, one way to analyze this circuit is write a differential equation, solve it. Or second one is use a graphical approach. I will use a graphical approach. I said Vi is equal to L di by dt. Instantaneous value of the input voltage becomes 0 at omega t is equal to pi. So L di by dt also should be pi. Sorry, L di by dt is equal to 0 at omega t is equal to pi. So L di by dt is equal to 0. It can happen only when di by dt is 0. So either it could be positive or positive maximum or a negative maximum. But then we know that current started increasing from 0. So it will reach a peak. Current can flow only in the positive direction. So therefore current reaches peak at omega t is equal to pi, because at this instant voltage across the inductor is also 0, input voltage is also 0. Vi is equal to L di by dt, that is equal to 0. So from 0 to pi, di by dt is positive. So therefore L di by dt is also positive. So area under the curve from 0 to pi is the positive L di by dt. We know that voltage average value of the voltage across the inductor is 0. Current reached peak at omega t is equal to pi. From omega t is equal to pi plus, instantaneous value of the input voltage becomes negative. So L di by dt also should be negative. So current starts decreasing. Where will it become 0? 0 to pi, it was increasing, reached peak at omega t is equal to pi. So it will reach 0 at omega t is equal to 2 pi. At that instant Vi is equal to L di by dt is equal to 0. So di by dt should be 0. Positive L di by dt should be equal to negative L di by dt. So diode conducted for the entire 2 pi radians. Beta is 2 pi, therefore gamma is also 2 pi. Average value of the output voltage is 0. Diode conducted for 2 pi radians, but then average value of the output voltage is 0. I have a question, how the diode started conducting beyond pi? Because input voltage becomes negative. A point to be noted that it is not the anode potential alone will decide the conducting state of the diode, it is the cathode potential also. If the cathode potential is less than the anode potential, diode has to conduct and diode will conduct. Okay. So what happens beyond pi? Input voltage may be becoming negative, but cathode potential, which is also equal to LdI by dt, current is also negative because di by dt is negative. So this polarity has, this terminal has become negative and this point has become positive. So therefore diodes continues to conduct till the current becomes 0. So remember, it's not the anode potential alone that will decide the conducting state of the diode, it is the cathode potential also. Okay. Here, because of the inductor, LdI by dt becomes negative, LdI by dt is negative because di by dt is negative. So negative, positive, this is also negative maybe, but this point is a bit more negative than this. A positive voltage or positive voltage of 1 volt also may appear across the diode, and hence it keeps conducting. Okay. So these are the various equations. I is equal to omega Vm divided by 1 minus cos omega t, V average is 0, power delivered to the load V average into I average is 0. Remember, diode conducted for 2 pi radians, average power is 0. In the previous case, diode conducted for pi radians, average power is finite, V average into I average. V average in the previous case is Vm by pi. Okay. Third case, now we will add, we discussed R, we discussed L, now we will see RL. Again, diode starts conducting at the positive 0 crossing. When diode starts conducting, output voltage is equal to the input voltage, and the circuit equation is R into I plus LdI by dt is equal to Vi, that is equal to Vm sin omega t. First order differential equation that has to be solved. What is the general equation? Sorry, what is the general solution? Has a sinusoidal component and an exponential term. Z is given by this term, phi is tan inverse omega L by R. What are the initial condition? When omega t is equal to 0, I is equal to 0, you solve it. This is the general equation, this is the solution for the current. Okay. Load is purely resistive, it reaches current reach maximum at omega t is equal to pi by 2. Load is purely inductive, current reach maximum and omega t is equal to pi. So if the load is RL, current will reach maximum somewhere in between pi by 2 to pi. Where it will reach maximum, it can be determined by solving the equation, the above equation. But I know that when current is maximum, voltage across the inductor is 0. So at this instant, the value of the input voltage is I max into R. Is that okay? When current is maximum, the instantaneous value of the input voltage is I max into R. So this point, this magnitude could be or is I max into R. Beyond that, current starts decreasing, but then current is always positive, it is flowing in this direction only, current cannot reverse, this is a positive direction of current. So I into R is always positive. LdI by dt, now di by dt has become negative, so this point becomes negative, this point has become positive. Current starts decreasing at omega t is equal to pi, instantaneous value of the input voltage is 0, but then current is still flowing in the load. So I into R, so LdI by dt should be 0. KVL has to hold good. Beyond pi, input voltage becomes negative. And since there is an inductor in the load circuit and current is decreasing, this current continues to flow beyond pi. That is because L di by dt has become negative. Cathode potential is less than the anode potential if I assume the diode to be non-ideal. If it is an ideal, cathode potential is equal to the anode potential. For non-ideal diode, this difference could be of the order of 1 volt. So current continues to flow till it becomes 0. Till the current becomes 0, input voltage is equal to the load voltage of V naught. Vi is equal to V naught till I becomes 0. So once the diode turns off, the entire input voltage appears across the diode. So this is the diode waveform, voltage waveform, till it starts conducting again in the next half. What is the average value of the output voltage? You need to find out, you have to integrate it. It is given by Vm by 2 pi into 1 minus cos beta. What are our observations? We found that when gamma, for a purely resistive load, diode conducts for pi by 2 radians, diode conducts for pi radians. When the load is purely inductive, diode conducts for 2 pi radians, and for a RL load, diode conducts for a duration is greater than pi. So gamma increases with an increase in L, but then average value of the output voltage decreases with L. Why? It's because beyond pi we are applying a negative voltage to the load. That is why average value of the output voltage decreases with increase in gamma beyond pi. What is the significance of gamma? Why the load current should be continuous, or why there should be a finite current in the load? What happens? Consider a simple case. I have a DC motor. Torque equation is K into phi into Ia, and the equation is J d omega by dt plus b omega plus TL is equal to T. T is the torque developed by the motor, load torque, frictional torque, J is the moment of inertia. So if I neglect the frictional torque, d omega by dt is equal to T minus TL divided by J. So at steady state, d omega by dt is 0. It is possible only if T is constant. In other words, if T varies with time, d omega by dt also will vary. When T will vary with time, either IF or IA or both. If they pulsate, TE also pulsate. So in order to have a constant TE, we should have a constant value of IF and a constant value of IA. So it is always desirable to have finite IA, if not a constant IA. Okay. Just by increasing L, we found that gamma may be increasing, but then load voltage, average value of the output voltage decreases. So just by increasing L may not be a solution for these circuits. What next? Is there a way out? I think so. There is a way out. What is that? Consider the circuit. A switch, switch can be closed to 1, 2 or 3. Initially I will close it to switch 1. What is the circuit equation? This is the circuit equation. R into I plus L di by dt is equal to V. We have studied this circuit. After some time I would like to open the switch. Either I will close it to 2 or I will close it to 3. What happens if I close it to 2? Voltage applied to the load is 0. So current decays in this fashion. The circuit equation is Ri plus L di by dt is equal to 0. Forcing function is 0, current decays slowly. Whereas in the second case, forcing function is negative. So current decays fast. So by applying a 0 voltage to the load, I have achieved two things. Current decays slowly, so in other words beta increases, but then I am not applying a negative voltage to the load, unlike in this case. So my average voltage remains constant even though my beta is increasing. Whereas here, since I am applying a negative voltage to the load, current decays faster plus the average voltage comes down. So therefore, it is possible to increase beta, also increase V naught. At what cost? Of course, nothing comes for free. If you are ready to spend something, you will get there will be a solution for every problem that you have created. Okay, that is the law of nature. Yeah, let's see. Consider a case. In the previous case, there was only one diode. I am connecting another diode across the load. Okay. Positive half, only D1 can conduct. D2 cannot conduct in the positive half. Okay. So in the positive half, D2 is blocking, or D2 is off, D1 is conducting. We have this equivalent circuit: input voltage, diode, D1, R into I, R and L. Same waveform, current increases, reaches a peak somewhere in between pi by 2 and pi and starts decreasing. At omega t is equal to pi plus, this potential becomes higher than this potential, becomes negative. So if D1 conducts, a positive voltage appears across D2, which is not possible. So therefore, D1 turns off, D2 starts conducting. Okay. When D2 starts conducting, this point gets connected to the cathode of D1. So negative voltage is appearing across D1. So diode D1 turns off, or diode D1 cannot conduct. So our assumption of saying that D2 conducting in the negative half is proved. So beyond pi, till the current becomes 0, D2 conducts. And I told you that when the D2 conducts, voltage applied to the load becomes 0. So rate of decay of current, or rate of decrease of the current that is flowing through the load also reduces. Current slowly reduces. So average value is same as that of a purely resistive load, in the sense output voltage is equal to input voltage till omega t is equal to pi, and beyond pi it is 0. So average value is same as that of a purely resistive load. Beta is also increased now. Beta is also increased. Here the decay is very slow. depends on the time constant. And in the negative half, the entire input voltage appears across D1. So, voltage rating of both these diodes is same as the peak of the input. So, D1 blocks in the negative peak and D2 blocks in the positive peak. So, this D2 diode is also known as the freewheeling diode. It provides a path for the current to flow when D1 is off. Load is freewheeling through D2. Okay. Now, let us see, let us discuss about RLE load. The limiting case L is 0. So, we have R and E. Can the diode start conducting at the positive zero crossing? No. Now, we need to know what exactly is there in the load circuit. If the load is active, we need to know the load parameters. If the load is passive and if the current is discontinuous, we do not need to know, because diode starts conducting at the positive zero crossing. Now, even if there is no current here, cathode potential is E with respect to this point. So, no current, same potential, this point and this point are at the same potential. So, E is the potential with respect, E of the cathode potential with respect to the ground, and anode potential is Vi. So, diode starts conducting when the instantaneous value of the input voltage is E, and once the diode starts conducting, the circuit equation is Vi is equal to R into I plus E, or I is equal to Vi minus E divided by R, purely resistive circuit. So, these are the equations. When diode is on, output voltage, when the diode is on, Vi is equal to V naught, and when diode is off, V naught is equal to E, V naught is equal to E. So, from 0 to alpha, diode was not conducting, output voltage is V naught, diode starts conducting at alpha, Vi becomes equal to E again at pi minus alpha. So, diode turns off at this point. Okay. So, once the diode turns off, till it starts conducting again, V naught is equal to E. So, this is the voltage across, V minus E is the voltage across R. So, current is V minus E divided by R, is a sinusoid, reaches a peak at omega t is equal to pi by 2. P by 2. Okay. These are the various equations. Yeah. Now, second case. Now, we will make R is equal to 0. We have a diode, inductor and a battery. Same as in the case of RE load, diode starts conducting when instantaneous value of the input voltage is equal to E, because anode potential is Vi, cathode potential is E. So, anode voltage should be higher than or equal to E for the diode to conduct. So, once the diode starts conducting, the circuit equation is L di by dt plus E is equal to Vi. So, when diode starts conducting, when the diode is on, output voltage V naught is same as Vi. So, difference of input voltage and the battery voltage appears across L, and beyond alpha this voltage is increasing. So, therefore, currents also starts increasing. Where will it reach peak? Will it reach maximum when omega t is equal to pi by 2 as in the case of resistor? Of course, one way to write a differential equation and solve it. But if I use a graphical approach, I can say that current will reach maximum when Vi is equal to E at omega t is equal to pi minus alpha, because at this instant Vi is equal to E. So therefore, LdI by dt is equal to 0. In other words, I is equal to I max. So current started from 0, reached a peak at omega t is equal to pi minus alpha, and from there onwards it starts decreasing. Where will it become 0? Again, it depends on E and L. It can be determined by solving the differential equation. But I know that average value of the voltage across the inductor is 0. So this is positive L di by dt. So current becomes 0 at that instant, or this area should be equal to this area. At that instant, current becomes 0. Okay. So current continues to flow beyond pi minus alpha till negative LdI by dt is equal to positive LdI by dt. So that's a very basic concept. Average voltage across inductor should be 0. So diode turns off at beta. So in this case, I have shown that diode continues to conduct beyond pi. It need not be, it can happen anywhere beyond pi minus alpha. So till the diode is on, output voltage is equal to the input voltage. Load has no role to play. Remember, when the diode is conducting, input voltage and the output voltage are same. It's only when there is no current and if the load is active, in other words, if there is a battery there, you need to know the value of the battery voltage, or output voltage is equal to the value of V when the diode is not conducting. So it was not conducting from 0 to alpha, and it stops conducting from beta to again 2 pi plus alpha. In this region, Vi, this is the input wave itself. Okay. So this is positive LdI by dt and this is negative LdI by dt. Okay. These are the various equations that I have written. Vi is equal to E at omega t is equal to pi minus alpha. V naught is equal to E for 0 to for omega t in between 0 to alpha. These are the various equations. I is equal to I naught at beta when positive LdI by dt is equal to negative LdI by dt. Now what happens if I put a small resistor RLE? When the load is purely resistive, we found that current reaches maximum at omega t is equal to pi by 2. Of course, in both the cases it started conducting at alpha, where alpha is sine inverse E divided by Vm. In the case of LE load, in the case of EL load, current reaches maximum when current reaches peak at omega t is equal to pi minus alpha. So therefore, for RLE load, current will reach peak somewhere in between pi by 2 and pi minus alpha. It reaches peak here, current starts decreasing, and it becomes 0 when somewhere in between this region it becomes 0. Okay, it all depends on R, L and E. It's a bit difficult to determine now because there is R is also present. So till diode is conducting, Vi is equal to V naught. When diode is off, V naught is equal to E. So if the load is highly inductive and has a very small battery voltage, beta may be high, because if E is low, as E reduces, alpha reduces, because alpha is sine inverse E divided by Vm. As alpha reduces, the time available for the current to increase also increases. I mean, because current reaches peak somewhere in between pi by 2 to pi minus alpha. As alpha reduces, time for the current to increase also increases. And if I have a substantial value of L, wherein current cannot change instantaneously, and if I have a low value of E, this beta can be increased. Okay. But then beyond pi, we have a same situation, a negative voltage appearing across the load. So the moment the negative voltage appears across the load, average value of the voltage applied to the load also decreases, plus current decays at a faster rate. Somehow I need to stop this. What will I do? I will connect a freewheeling diode across the load. Okay. I have connected a freewheeling diode across the load. Till pi, the behavior of the circuit is same as before, no change. The waveforms also no change. From 0 to alpha, it is the input, it is 0 to alpha, it is E, because no current, so V naught is equal to E. From alpha to pi, assuming that there is some current flowing in the circuit, Vi is equal to V naught. In other words, V naught is equal to Vi. At omega t is equal to pi plus, the freewheeling diode starts conducting. So voltage applied to the load is 0. Diode turns off. Now. Source does not supply power to the load, but then since there is an inductor, the stored energy in the inductor continues, or stored energy in the inductor ensures the current to flow in the load beyond pi. So at beta, current becomes 0. So once the current becomes 0, voltage applied to the load becomes E. So difference is only from pi to beta. Pi to beta, voltage applied to the load is 0, becomes this one. Okay. See, all these circuits can be analyzed by writing the differential equation for various modes and solving them. Okay. I am not using that approach. You are free to do that. I would encourage you to write those equations and solve numerically. So this is what it is. I starts flowing. Now consider a case. Assume that load current is continuous. Don't ask me what sort of a load. It could be anything. I mean, it can be LE type or whatever. Don't bother. I may have a battery, I may not have a battery. Okay. Only thing is current is continuous. So if the current is continuous, either D1 should be on or D2 should be on. Okay, at any given time. In the positive of, we already proved that D1 conducts, and in the negative of, D2 conducts. So at any given time, one of the diode is on. So in the positive of, D1 is on, and in the negative of D2 is on. Okay. So when D1 starts conducting, so D1 starts conducting in the when omega t is equal to 0, or at the positive 0 crossing, diode starts conducting. So therefore, if the load is continuous or load current is continuous, diode starts conducting at the positive 0 crossing. Diode starts conducting at the positive 0 crossing, and D2 starts conducting at the negative 0 crossing. So even if I have a battery in the load and if the current is continuous, it does not matter, D1 starts conducting in the positive 0 crossing. Remember, even if I have a E here, that is because of L di by dt, because once the current has reached peak, in a RLE type of load, we found that current reaches peak between pi by 2 to pi minus alpha, and beyond that current starts decreasing. So L di by dt becomes negative. That will ensure the current to flow. So therefore, even if I have a battery here and if the current is continuous, diode starts conducting at the positive 0 crossing. Please do not say that you have a battery in the load, so that is why it cannot conduct till alpha. That is true only when current is discontinuous. If the current is discontinuous, we found that cathode potential of the diode is at E. So anode potential should be higher than or equal to E for the diode to conduct. That is why it starts conducting at alpha, which is equal to sine inverse E divided by Vm. So if the current is continuous, D1 starts conducting at the positive 0 crossing. An important concept to be remembered. Okay. So this is the proof. So here is the proof. So potential of A is potential of C in the positive of, I am assuming D2 is on. If D2 is on, see what is, when D2 is on, potential of B is equal to potential of C. So in the positive of, if this occurs in the positive of, a positive voltage appears across D1, because in the positive of, potential of A is higher than C, and if D2 conducts, this potential gets connected to B, a positive voltage appears across D1. So D2 cannot conduct in the positive half. D2 cannot conduct in the positive half. So if again I will repeat, if I is continuous, in the positive of D1 conducts and negative of D2 conducts, independent of type of load. So what are the conclusions? First one is the conduction angle or the duration for which diode conducts increases with load inductance. Second is, for the diode to conduct, voltage across the diode should be 0. Okay, is not only the anode potential alone will decide the conducting state of the diode. It is also the cathode potential. It is also the cathode potential will determine whether the diode can conduct or not. Use of freewheeling diode increases gamma. Why it increases? Because it applies a 0 voltage to the load. It applies a 0 voltage to the load. Therefore, decay process also, current decay process also, decay, the rate of decay also reduces. But then voltage applied to the load is 0. If there was no freewheeling diode, the voltage applied to the load beyond pi is negative. Average value comes down, decay process also faster. So we are achieving two things at the cost of one diode. Okay. So the next point is, if the current is discontinuous and if the load is RLE, the instant at which diode starts conducting is given by sine inverse E divided by Vm. Okay. And if the current is continuous, alpha is 0. Alpha is 0. It is independent of flow. That is because of L di by dt. These are the important concepts to be remembered. If I know the behavior of L, C with sinusoidal excitation, the study of power electronics is very simple, very simple. I would encourage you to use a graphical approach rather than the analytical approach. Writing a differential equation, solving it, anyone can do. If you try to use a graphical approach, it will give a better insight rather than writing a differential equation. Okay. So what did you do the entire class? We just used one simple KVL and our one equation, Vm sin omega t is equal to R into I plus L di by dt plus E. That is the most complicated equation. And I did not take any time in solving this equation. You can always solve that equation. I use a graphical approach. Somehow I like it more. And I encourage you to use this approach rather than solving using a differential equation. Thank you.